Much like polynomial inequalities, the best way to understand rational inequalities is to start by looking at a graph. In this case, we have a graph of the function y equals x minus 1 over x minus 2, and we are interested in looking at where this is greater than or equal to 0, which we will interpret as above y equals 0 or above the x-axis. So let's start by highlighting the parts of the graph that are above the x-axis. This whole piece here in the upper first quadrant is above the x-axis, and we know it stays above because of this horizontal asymptote. On the other part of the graph, it looks like right here at x equals 1, where we have a 0, is where the division between above and below occurs. And the above part is this piece, which also has an arrow here. Now I will consider the form of the inequality, which is inclusive, which means where the function is equal to 0, we're going to include. So I will go ahead and make a solid dot at x equals 1, and then I'm going to translate this set into x values. We start at negative infinity and come up to positive 1. I'm going to put a square bracket at positive 1 because I can see that I included that point in a sort of solid dot there. This starts over again at x equals 2, but x equals 2 is not in the domain. That's a vertical asymptote of the function. So where I start this again, I'm not going to include that value, but I can see that it continues off to the right from here. So the second part of this inequality is going to start with a round parenthesis at 2 and go up to positive infinity. This is the first case that we may have seen in which the bracket style doesn't match the inequality. We have an inclusive inequality, but we still have a round parenthesis instead of a square bracket because of the fact that 2 is not even in the domain of x minus 1 over x minus 2, so it can't be in the solution set to the inequality either. Now that's not to say that it can't show up as a number in the solution set. It's still a boundary value, but the value x equals 2 is not included in this solution set because we don't have a square bracket there at x equals 2. So note from this example that we can now summarize what the boundary numbers are. In a polynomial inequality, we said the boundary numbers were the zeros of the polynomial. Here, the zeros of the function are still boundary numbers, but the zeros of the function are specifically zeros of the numerator. Anything that makes a numerator of a rational expression 0 is going to make the whole expression equal to 0. We can also see that the vertical asymptotes are boundary numbers, because at a vertical asymptote, a function can change from positive to negative or from negative to positive. In this case, we had a vertical asymptote at x equals 2, and we can see that on one side the function went down, on the other side the function went up, and that's how it changed from negative to positive on both sides of x equals 2. So values outside the domain turn out to be zeros of the denominator. So even though the reason is fairly complicated, the rule is very simple. All we do is we find all the zeros of the numerator and all the zeros of the denominator, and we use those as our boundary values, meaning that we mark them on a number line. So let's go ahead and look at a rational function that's given to us without a graph and follow this process. The boundary numbers are zeros of the numerator and zeros of the denominator. My numerator is x minus 3. That is equal to 0 if x is equal to 3. My denominator is x plus 1. that is equal to 0 if x equals -1. So x equals +3 and x equals -1 are my boundary values. I'm going to mark these on a number line. -1 is to the left of +3, so I'll put it first. And while I'm at it, I'm going to mark each of these numbers with whether it itself is part of the solution. This is an inclusive inequality, so that means zeros of the function are included in the solution set. 3 is a 0 of the numerator and therefore is a 0 of the function. On the other hand, zeros of the denominator are never in the domain. So that means that even though -1 is a boundary value and might be an endpoint of an interval, it cannot be in my solution set. So I draw an open circle at -1. I'll just do this now so that I'll know later when I go to set up my bracket types which ones to include with square brackets and which ones to just leave simply as parentheses. Okay, now it's time to pick representative values from each interval. Something to the left of -1, I'm going to choose -2. Something between -1 and +3, I'll choose 0. And something to the right of 3, I will choose 4. And now I will do my sign analysis. Setting up a table to analyze the signs, I'll put these 3 representative values, -2, 0, and 4, under x, and I'll figure out the sign of each of these factors. If x is -2, x minus 3 is negative. X plus 1 is also negative. So my overall sign would be a negative divided by a negative. It doesn't really matter whether it's division or multiplication. We're still going to just count up the negatives. If we have an even number of negatives, which is the case here, then we'll say positive. And if we have an odd number of negatives, then we'll say it's negative. If x is 0, we have -3 divided by +1, so the overall sign is negative. And if x is +4, both factors are positive, and therefore the overall sign is positive. So copying this sign pattern over to my number line, I can see that it goes plus, minus, plus. I will now think about what intervals to include. This inequality says less than 0. Numbers that are less than 0 are negative. So I'm only going to include the one negative interval here, which goes from -1 to +3. I know that it excludes -1 because -1 is not in the domain, and I know that it includes 3 because 3 is a 0. So I am now ready to write my solution set as the interval from -1 with a round parenthesis to +3 with a square bracket.